So hi everyone. So today we will start our tutorial 4. So that will be mainly consist about some discussion about the negative temperature and some discussion and some conceptual overview about what is a microcanonical ensemble. So so before starting that, let me recapitulate what we have discussed in our previous tutorial 3. Okay. So let me first recap the things that we have learned. Uh, so in our last tutorial, first we have discussed about the internal energy, right? So internal energy. So how we have derived the expression of internal energy? So basically we have these energy states E0, E1, E2, E3, E4 and likewise. And each energy states there are a population of particles in 0, N1, N2, N3 and similar way. So if this is the way the particles are distributed among the energy levels, then the total energy will be E would be summation over I Ni EI. That is like N0, I runs from 0 to N. So N0 into E0 plus N1 into E1 plus N2 into E2, likewise. Okay. Basically, the number of the energy state multiplied with the number of particles that are exist in that particular energy state. Okay. Now, also we know this distribution of the particles at a particular temperature at a particular state is related by this Boltzmann distribution, right? Where Ni, that means the particles at higher energy state will be related like this with the temperature. Okay, Q is the partition function. Yeah, this is the Boltzmann distribution. We have learned it in the in our discussions, right? Previous discussions. So this is called the Boltzmann distribution, right? And from there itself, we have derived the expression of the total energy, right? That is like this, equal to minus n by q derivative with respect to beta to the power summation over to the power minus beta ei. Right, here q is basically is the partition function. Q is the partition function. Okay. So this is how like we have derived the expression of the total energy. We have also can write this in a more compact way like this. N by q dq dbeta. Okay. This is a way of writing the total energy of a system. Now from if you got the information of the total energy, then from there you can easily calculate, right? So basically internal energy U is basically the total energy of the system plus the internal energy at t equal to 0. Okay, so if you add the if you want to calculate internal energy at a particular temperature, so in that case you have to just basically add the total energy of the system plus the internal energy at 0. If its internal energy is 0 at equal to 0, then the internal energy will be simply equal to the total energy of the system. So general expression of internal energy is this, that means U0 minus n by q del q del beta at constant. So these are all constant volume. Okay. Yeah. So this is the basically the general expression of the internal energy of a system at a particular temperature. Okay. Yeah. Uh, Now, using this formulation, we have first solved some problem where like there are energy states with certain degeneracy. Uh, like the system consists different energy states, and each energy state consists of degeneracy. So in that kind of system, how can you calculate the uh, total internal energy of a system at a particular temperature? So in those kind of scenarios, we have calculated the internal energy. Next, we have derived the what is the expression of beta. Okay, beta is 1 by kBT, right? But in our in our previous discussion, we are just simply using this result, right? But we do not explicitly derive how this beta equal to 1 by kBT is coming, right? So in our last tutorial, we have derived how this beta equal to 1 by kBT is coming. So how we have done it? We basically compare the internal energy of a ideal gas, uh, both by from using kinetic theory. We have derived basically the internal energy of an ideal gas by using the kinetic theory of gases and by using the partition function. And since we will be getting the same value, then like we have compared the values of the internal energy, and from there we have got the expression of beta. Okay, so let me just tell you briefly how we have done it. So we basically calculate the internal energy using this formula, N by Q del beta constant V. So for ideal gas in 3D, we know the partition function is like this: V equal to lambda Q, where lambda is a thermal wavelength. This expression we got from particle which is trapped inside a 3D box, right? Translational partition function of a particle that is trapped in a 3D box, right? So that would be similar. That situation is actually same with the case of an ideal gas, right? Ideal gas also you can consider it as a particle which is trapped inside a 3D box. Okay. So for that, so that's why we are using the same translational partition function here also. And by doing that, we are getting the internal energy expression like U equal to U0 minus so basically U minus U0 we got 3n by 2 beta by 1 by lambda into lambda, so 3n by beta. This is the value of the internal energy we got by using the partition function formulation. And also we know for 3D gas, 3D ideal gas, from the kinetic theory of the gas, you already know total energy is 3 by 2 nRT. So in this case, U minus U0 would be also 3 by 2 nRT. This we got from the kinetic theory of gases. Okay. So now by comparing these two, 1 and 2, we got the expression of beta as 1 by kBT. Okay. So this we got comparing 1 and 2. So this is a way you can get the. There is also several other ways, but this is the way that we have used to get the expression of the beta. Next thing, we have calculated the specific heat. Okay, so so we have calculated specific heat. Basically, is a very important quantity in thermodynamics. So basically, in materials, the specific heat basically gives you a very important quantity to basically interpret the thermal behavior of that particular material. Okay, so if you know if you calculate a thermodynamic quantity at a particular temperature, then using the specific heat you can calculate the same thermodynamic quantity at a different temperature. Okay, you don't need to do the experiment. Okay, but by using the specificity you can easily calculate it. Okay, that's why specificity plays a very important role. So we have calculated like the expression of CV is basically this. CV is basically the heat that is required if you this is the expression of C. So C has two types of variant. One is specific just at constant volume, that is this dq by dt at constant volume, and Cp at constant pressure, that is dq by dt at constant pressure. Okay. So that is basically the heat. If you want to increase the temperature of a system by dT, that if the amount of heat that is required is dq, then specific heat is basically dq by dt. Okay, and you have to calculate it by taking either volume as constant or pressure as constant. Okay. So the basically if you use the first law of thermodynamics, then this expression of CV will be reduced to dq dt. You can write it like this: del u del t by constant volume, or for constant pressure you can write it also like this. H is the enthalpy, del H del T at constant pressure. So this is the expression of the specific heat that we have derived earlier. For ideal gas, you know, U is basically 3 by 2 nRT. So CV would be simply del U del T. That means 3 by 2 nR. Okay. This is for ideal gas, which means it's a constant value. Okay. Specificity basically constant value. So this is some results, and also the next thing that we have calculated is the entropy. ds, you know from classical thermodynamics, ds is basically dq reversible by t for a reversible process definitely. So from there we have calculated the expression of the so dq reversible, you can write it as du by t at constant volume. Now from here we have calculated the du. We have like du in terms of energy and number of particles. Then we have like basically substitute the expression of du into here in this equation. Now from there, after doing several derivations, a long derivation, we got the expression of the entropy in the differential form, but ds equal to k d of ln w, where w is basically the weight of the configuration. This basically means the in the very first lecture that we have discussed, like if there are n numbers of particles is there, total number of particles is n, then out of this n, if like n0 number of particles is in state 0, into n1 number of particles in state 1, into number of particles in state 2. So likewise this, if the particles are distributed among the states, then the weight of this particular configuration will be w equal to n factorial by n0 factorial, n1 factorial, n2 factorial. So like this, okay, but n0 plus n1 plus n2 plus dot 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 equal to n, right? Capital N, right? So okay, so this is basically the way. If you basically know, that means if you basically know the weight of a configuration, then you can easily calculate from there the total entropy of the system. So the last thing that we have done in the last tutorial is for a system, for a three-level energy system, E1, E2, E3, we have first calculated the partition function, and then from the partition function we have shown how to calculate the specific heat of the system. Then we have calculated the entropy of the system. These are basically the problems that we have done in the last tutorial. So now in today's tutorial, Uh, we will start with a problem. Okay. Start with a problem of a system. Uh, there is also expression of entropy. Okay. One second. It will write it here. So expression of the entropy also you can write in terms of the internal energy and partition function. So that expression is also very useful. Uh, this is u minus u0 by t plus nk. This is also a very useful expression of the entropy. This expression also we will use in our later stage. Okay. So now we'll as we have this as I have told before that we will start today's session with a problem. So the first problem is question number 1. Consider a system with 4 energy levels. Ground state is equal to 0, which is triply degenerated. This is G0 equal to 3. That means second is the first excited state. First excited at E1, and E1, the first excited state, is basically doubly degenerate. Doubly degenerate is G1 equal to 2. Second state, second excited state at E2, which is non-degenerate. Here G2 is basically 1, and third excited state at E3 is triply degenerate. In this case G3 equal to 3. Okay. Basically the system has 4 energy state, and each energy state had some degeneracy associated with it. The first has triply degenerate, second has double degeneracy. This, the third one is the second excited state is non-degenerate. The fourth energy, third excited state E3 is triply degenerate. Okay. Now we will first, so the rule of thumb is first we have to calculate the single particle partition function, because this is a particle as the problem is okay, so the problem is for n non-interacting identical particles. Okay. Derive expression for the internal energy UT and the entropy ST. Okay, so basically the thing is this four energy states. So in the problem, it's mentioned the particles are non-interacting and identical particles, which makes actually which makes us things a bit simpler for us. Basically, we will first do this whole thing for a single particle system. Then we can, like, as the particles are identical and non-interacting, so we can, from the single particle system, we can easily transform the results to a n particle system. Okay. So the first steps towards this is we will calculate the single particle partition function, right? That's the way of any kind of, I mean, any kind of problem, I mean, this kind of problem that you're dealing with, right? First thing that you have to calculate is the partition function. Okay. So Q is basically the partition function is summation over J Gj into e to the power beta Ej. Now J is the index of the energy state, and Gj is basically the degeneracy associated with the energy state Ej. Okay. Now from here, the Q would be the first energy state energy E was 0, E0 was 0. So G0 into to the power beta E0 plus G1 to the power beta E1 plus G2 to the power beta E2 plus G3 to the power beta E0. Now here E0, G0 is 3, so triply degenerate. So 3 into E0 is 0, right? So 3 into 1. 3 into 1. So e to the power 0 is basically 1. G1 is 2, right? So 2 into e to the power beta. E1 is, so E1 is just E1. Okay, they kept it as E1. So 2 into e to the power E1 plus G2 is 1. So 1 into e to the power beta E2 plus G3 is 3. So 3 into e to the power beta E3. This is the expression of the translational partition function of the system. Now, as we have derived the translational partition function of the system, now from it we can calculate, the first thing is the internal energy, right? So the internal energy is basically internal energy. So U is the internal energy expression. So here for our simplification, we consider the internal energy is equal to the total energy of the system. That is nothing but n equal to del del beta of L Q. And we are simply multiplying it because we are deriving this whole thing for n particle system, right? So that's why just multiply the del beta del in ln q. Del del beta of ln q into n gives you the partition function for n non-interacting identical particle system. So so now so this we can write it like this, nq into del q by del beta, and this way also you can write, right? So now first we will simplify del q del beta. Okay. So del q del beta, if you do del del beta of q is 3 plus 2 into to the power beta epsilon 1 epsilon index 1 plus e to the power beta epsilon index 2 plus 3 to the power beta epsilon 3. Now for do the derivative, this simply gives you 2 into minus 2 into epsilon 1 e to the power beta epsilon 1 minus epsilon 2 e to the power minus beta epsilon 2 plus minus 3 into epsilon 3 to the power minus beta epsilon 3. This is the expression minus, if we take common in the left hand side, but this gives you 2 epsilon 1 to the power minus beta epsilon 1 plus epsilon 2 to the power beta epsilon 2 plus epsilon 3 to the power beta epsilon 3. Okay, so this is the del q del beta expression you will be getting, right? So now the next thing is, as you got the expression of del q del beta, now simply you can derive the expression of internal energy, which is nothing but U equal to N into. So first del Q del beta I am writing minus 2 epsilon 1 to the power beta epsilon 1 plus epsilon 2 to the power minus beta epsilon 2. Then 3 into epsilon 3 e to the power beta epsilon 3, and you have to divide the whole thing with the expression of the partition function, right? So that is 3 plus 2 into e to the power beta epsilon 1 plus e to the power minus beta epsilon 2 plus 3 into e to the power minus beta epsilon 3. Now minus minus will simply cancel. That gives you the final expression of the internal energy, that is this epsilon 1 to the power minus beta epsilon 1 plus epsilon 2 to the power minus beta epsilon 2 plus 3 epsilon 3 to the power minus beta epsilon 3. This whole thing is divided by 3 plus 2 into to the power minus beta epsilon 1 plus divided beta epsilon 2 plus 3 into to the power minus beta epsilon 3. So this is basically the expression of the internal energy of the system. Okay. So now, first we have derived the internal energy of the system. The next thing in the problem, so after the internal energy, you have to calculate also the entropy of the system. Okay. So how can you calculate the entropy? So we will use the formula that we have discussed earlier. This formula, how this using, if you have the result of the expression of the internal energy and the partition function of the system, from that, using this formula, you can easily calculate the entropy of the system, right? So in order to do that, okay, so let me first write this thing. Okay, just let me copy it. This thing also. Yeah, this is fine. So now, internal energy expression you already know. Now we have to plug it here, the expression of the partition function. Okay, so we will do that. So the S would be U by T plus NQ. ln Q is the expression of the partition function. That would be, this is the basically expression of the partition function. So 3 plus 2 into e to the power minus beta epsilon 1 plus to the power minus beta epsilon 2 plus 3 into e to the power minus beta epsilon 3. Now here, if you also substitute the expression of the internal energy, then it would be, first let me rewrite this one, epsilon 1 plus e to the power minus beta epsilon 2 plus 3 into e to the power beta epsilon 3 plus u by t. So that would be n by t. So this whole thing basically n by t into 2 by epsilon 1 e to the power beta epsilon 1 plus epsilon 2 e to the power minus beta epsilon 2 plus 3 into epsilon 3 to the power minus beta epsilon 3. This whole thing is divided by 3 plus 2 into the power minus beta epsilon 1 plus e to the power minus beta epsilon 2 plus 3 into the power minus beta epsilon 3. This is basically the expression of the entropy. you can write it in a more simplified way. You can take kb as common because beta is 1 by kb, you know. Then you can write this whole thing in terms of beta, not you can basically substitute the temperature terms into the as a beta. So ln 3 plus 20 to the power minus beta epsilon 1 plus e to the power minus beta epsilon 2 plus 3 into the power beta epsilon 3 plus the beta will be coming here into epsilon 1 to the power beta epsilon 1 plus epsilon 2 to the power minus beta epsilon 2 plus 3 epsilon 3 to the power minus beta epsilon 3. This whole thing is divided by 3 plus 2 into 2 to the power beta epsilon 1 plus e to the power beta epsilon 2 plus 3 into 2 to the power beta epsilon 3. Okay, so this is the basically the expression of the entropy of the system. Okay, so let me just revisit what we have done. So basically we have been supplied here that there are four energy states are there: ground state, first, second, and third excited states. Each state has some degeneracy associated with it. The first one has triple degeneracy, the second one is double, third one has no degeneracy, and the fourth one has triple degeneracy, right? So we have been asked to calculate for n numbers of non-interacting identical particles, what is the expression of internal energy and entropy? So according to the rule, we will first calculate what is the partition function of the system and got the expression of the partition function here. From that, from if you able to know the expression of the partition function, from there it's basically this formula which will basically gives us the expression of the internal energy from partition function. So we have done the derivative of the partition function with respect to beta, and from there we got this expression of the internal energy. After calculating the internal energy, our next task will be calculating the entropy. So this is basically how the entropy is related with the internal energy and the partition function of the system. Okay. So for our convenience, we are considering this u0 as equal to 0. So the entropy is simply equal to u by t, and u is nothing but the total energy. And we are first substituting the q here, and we also derive the internal energy expression in our previous derivation. This is the expression of the internal energy. After substituting those two quantities here in the expression of the entropy, we get a like total result for the expression, like the derivation of the entropy. Okay. Okay, so this is a type of problem. So now the next thing that we will calculate, that we will do is the thing called negative temperature. Okay. So what is basically negative temperature is? Okay. So let me write it. The concept of negative temperature. So this is basically a kind of a very much intriguing theoretical concept, you can say, because in experimentally we have reached a certain level of temperature. Okay. And below to that temperature, it's not like experimentally not yet find out. Okay. And here temperature means T means here we are doing it in Kelvin, okay, not in degree of centigrade, it's Kelvin, okay. So T equal to -1, -2, -3, -100, that means -1 Kelvin and -100 Kelvin. So how can we achieve the negative temperature? Okay. Conceptually. So so let's start with the system. Let's suppose there are total number of particles n, and out of this total particles equal to n, and and out of this n particles, let's suppose n plus number of particles is in state E and n minus numbers of particles in state 0. So there are basically two energy states, n plus and n minus. Okay. So according to the Boltzmann distribution function, we know n plus is basically n into e to the power minus epsilon by kt by q, and n minus is basically n by e to the power 0 by kt by q, right? This we know from Boltzmann distribution, right? Boltzmann distribution. So n plus and n minus ratio would be then simply e to the power e by kbt, right? This is the expression of the ratio of n plus and n minus. N plus is the particles that is in energy state E, and n minus of the particle that is the ground state. So now what you can do now to find out the temperature. Temperature, we want to find out negative temperature, right? So we have to write this whole thing. As an expression of n plus and n minus. So we will basically write this whole thing where the temperature would be on the left hand side, right? So how we can do that? We have to write the whole thing as an expression of n plus and n minus. So we'll take log in the both side. This gives you minus epsilon kt. So now from here, epsilon kt, you can like change the numerator denominator here inside a log, that it gives you the minus term, and minus minus will become plus. This will gives me this, and from here you can write t simply e by k, and the denominator it will be the log of n minus n plus. Okay. So this is basically the expression of the temperature we got here, right? Now from here, we want to find out the temperature. We want to find out the condition for which the temperature would be negative. So according to this expression, the only way the temperature is negative is when this inside this logarithmic, this whole logarithmic term becomes negative, right? And when this logarithmic terms become negative, when the n minus by n plus is less than 1, right? So that means n plus would be greater than n minus. Okay, this is the condition to obtain the minus temperature. So this actually, what does that physically means? Physically means the population of the upper excited state should be higher than the lower state. Okay, this is the one and only option to get the negative temperature in this kind of a two-level system. Okay, so this physically means that the population of the upper state to exceed that of the lower state. Okay, then the temperature must have a negative value. Okay. So this is the condition to obtain the negative temperature. Okay. So that means whatever quantity that we have derived right now till now has this concepts is has this like concept of internal like the negative and positive temperature associated with it, right? Like all the expression is, that means all the expression is valid for both positive, I mean all thermodynamic expression that have derived till now will be valid for both the positive and as well as for the negative temperature. Okay. So there is like so um, in order to get this kind of negative temperature, there are various ways are there, like in experimental literature, to uh, get this to achieve this basically negative temperature state. So if you basically has to able to do, so it's basically you cannot able to get this kind of very low temperature in a finite number of steps. You have to do it in an infinite number of steps in order to get this kind of low temperature. Uh, so let's suppose do it. So let's do it in a in the case of a spin particles. Okay. So as we know, when the particles are, let's suppose there is a system that consists of spin up particles. Okay. Spin up particles. So either the spin, so there are only two orientation is possible. One is spin up, this is the up state, and this is the down state. Now let's suppose the system in which the this orientation is like not in a ordered cell, like this. As you can see here, the spins are not in a ordered state. So that means the entropy not ordered. And when the particles are ordered with each other, so this is has high entropy, right? And this has low entropy, right? This is ordered. Okay. So now, what we will discuss. So apart from the ordering, there is also effect of temperature, right? Like if you increase the temperature, whether it's a ordered system or a disordered system, if you increase the temperature of the system, in an ordered system also more particle will order themselves in a random way, right? So this will directly increase the entropy of the system. Okay. So now so one way to make the system in a order format, that if you put this kind of a this kind of a not ordered system in external field, then this system becomes basically ordered, right? At some particular temperature B, when B is not equal to 0 in external field. Basically all the system spins are basically uh, in a ordered way. Okay. So now let me draw the entropy versus temperature. So yes, this is the unmagnetized, this is the magnetized. So in this case B is not equal to 0, this is B equal to 0. This is the temperature and this is the entropy. So when B is equal to 0, it's unmagnetized basically. So when you increase the temperature, its entropy will change in a much more rapid way compared to the case where the field is not equal to 0. That means that there is some inherited ordering is exist in the system. So that's why its change in entropy with the temperature will be much slowly compared to the unmagnetized one. Okay. So now, so basically, let's suppose we will start from a system that is on point A. Okay. Now we want to basically shift the system to a very uh, low temperature state. Okay. So how can we do that? Okay. So we will first do isothermal magnetization. Okay. So isothermal magnetization means the change like so isothermal means the change in temperature would be zero. So dT will be zero in this case. Okay. So if you do the isothermal magnetization from state A to state B, that means the change in temperature will be zero, but the system will magnetized. So that means it will shift from point A to point B like this, right? Now the next thing we'll do is called the adiabatic demagnetization. Okay, so adiabatic demagnetization means so this is called isothermal magnetization. The next thing that we'll do is called this the adiabatic demagnetization. The adiabatic means dq is basically equal to 0, and if you know, for a reversible process ds is directly related to the dq from this relation. So if dq is 0, that means ds would be simply become 0. So for that, so isothermal the adiabatic demagnetization means it will move the system from B to C like this. This is a straight line. Okay. So this is means the adiabatic demagnetization. So you can see the system moves towards a much lower temperature. Now if you repeat the process again and again, this will basically shift the system into like more cooler temperature. But the more if you want to change the temperature to a much cooler value, then you have to do you have to repeat this whole step infinite amount of numbers. Okay. Then only you can get the coolest temp like the the cooler temperature. Okay. So this is basically the experimental over here. So now let me discuss some problems. Okay, regarding this negative temperature. Okay. So let me, before discussing the problem, let me just tell you once again what we have learned. So we are starting with the concept of negative temperature. So first what we have done, we have like taken like for a two-level system E and 0. How can we theoretically achieve the negative temperature? So we put n plus number of particles in state E and n minus number of particles in state 0. From there we have derived the ratio of the n plus and n minus, and from there we got the expression of the temperature, which in that expression of the temperature we got epsilon by k in the numerator, and a ln of n minus by n plus we got in the denominator. And from there we what have derived if n minus by n plus is less than 1, that means the number of particles in the excited state exceeds the number of particles in the ground state. In that case we got the temperature is negative. Okay. So this is basically how the concept of the negative temperature is coming, and from there we basically discussed experimental point of view how we basically get this kind of negative temperature. So how you will got. So we basically starts with the system. This is basically we start from the entropy temperature response of a magnetized and demagnetized system. So from there, let's suppose a system is demagnetized here at a particular temperature in point A. So what we do, we first do isothermal magnetization. So dt is 0. So particle basically magnetized from system A to system B, point A to point B, and from there we adiabatic demagnetize. We do the adiabatic demagnetization. Adiabatic means d equal to 0. So the state will shift from B to C. Here now we will repeat this whole process again, isothermal magnetization and adiabatic demagnetization, then again like this. So if you do it an infinite amount of time, then only you can achieve the closest. The more number of times you will do these whole steps, the more closer you will go to the cooler temperature. Okay. So this is it. So now the next thing we will discuss. So we'll take a system with degeneracy. We will make the system in contact with a temperature, with a inverse temperature. The whole system in contact with a thermal bath which has an inverse temperature, and then we will see what happens to the system. Okay. So the setup is like this. So two level system in a negative T bath. Okay. So levels 0 and E with degeneracy G0 and G1, system in contact with a bath at inverse temperature beta less than 0. Okay. So beta less than 0, that means the T also should be less than 0, right? So yeah. Okay. Because KB is always greater than 0, right? KB is the Boltzmann constant that cannot be negative. So the T should be less than 0. Okay. So for this kind of system, we'll check what happened if we do some if we encountered such kind of setup, what will happen to the system. So we know this is the similar technique with system 0E. This has degeneracy G0, this has degeneracy G1. So the system with degenerate G0 has the uh, number of particles n1, and system with zeros the particles n0. So n1 has basically G1 to the power minus BE into in by Uh, so it would be like this. Just yeah, it would be Q here. So N1 by N is basically N is the total number of particles. Is basically this. Similarly, N2 by N is basically G0. Sorry, N0 by N is basically to the power minus beta into 0 by Q. So that means Ny by N0 is G1 by G0 into e to the power beta epsilon N1 by N0. This is the expression of N1 by N0. That means the fraction of particles in the first excited states to the fraction of particles in the ground state. Okay, this is the basically the fraction. So now, if beta is negative, thermal bath that is connected to the system is negative. So that means this e to the power beta epsilon is also negative. So beta, so sorry, if beta is negative, this means e to the power minus beta epsilon. This is basically greater than 1, right? Because this whole thing is greater than, sorry, this whole thing is, so yeah, greater than 1. So beta is less than 0. So that means negative, negative, positive. So this whole thing is greater than 0. So which makes this e to the power minus beta epsilon is greater than 1. So that means n1 by n0, sorry, this is small letter. N1 by n0 would be greater than 1. So that means n1 is greater than n0. Just how we talked about, like in our derivation, conceptual derivation also we have discussed, right? It's only possible when the number of particles at higher excited state exceeded the number of particles in the lower excited state, right? So let's take an example, like if suppose G0, for simplicity let's consider G0 is equal to G1, though both the states have same number of degeneracy. And if we put temperature of the bath is at minus 150 Kelvin, okay, and let's take epsilon by K, so here, yeah, so let's take epsilon by K 300 Kelvin for the timing. For let's suppose energy state by K, like energy state has some value, this kV basically has some value like 300 kV, something like this. So epsilon by kV you can write it like 300 Kelvin, like this. Now if you substitute these two expression into the here, so N1 by N0 is G1 by G0 into to the power minus epsilon to the power beta epsilon, right? So now here, if you put epsilon by kV equal to 300 and T equal to minus 150, then you will get, right, G1, G0 will cancel, this gives you 300 by 1 minus 150, so that gives you a square, so which is approximately 7.39. So N1 is 7.39 times of N0, right? This would happen to the system, okay, if you put a negative, a thermal bath with negative temperature connected with the system, okay. So next thing we will discuss in terms of Carnot engine, okay. So, Carnot engine. So we will now discuss what happens to Carnot engine if you like put one end of the Carnot engine. Let's suppose the part which is supposed to attach with the hotter bath. If you, instead of the hotter bath, if you connected that part with a bath which has a negative temperature, then what basically that negative temperature bath will, how basically the negative temperature bath will affect the Carnot engine, that we will now explore, okay. So Carnot with negative temperature reservoir. Okay. So let's take the Carnot engine. So as we have discussed, let's take the Carnot engine. This is, let's suppose, a Carnot engine. It basically drives like this, right? It takes the temperature. Let's take the heat QH from the water bath to a cold TC QC, and in between it does some work. Okay. This is basically the principle of a Carnot engine, right? Now here what we'll do, instead water bath, let's take TH equal to something like, let's suppose, minus 200 Kelvin, and T cold is like 300 Kelvin. Okay. Now what will happen? Now what will simply happen? The expression of eta we know. Eta is basically TH minus TC by TH. So if you write it like this, now TC by TH. So now here, if you put the expression, put the values of TC and TH here, so it will gives you 1 minus TC is 300, TH is minus 200, which gives you 1 plus 3 by 2, 5 by 2, which is greater than 1, right? So that basically signals that the heat in from the hot reservoir, heat out to cold. Okay, heat in from hot and heat out from cold. Okay, so it's like the opposite thing. With a negativity reservoir, you can like the exact work while cooling both the reservoir and negative T body decrease in energy when it gives off the heat. Okay. Yeah, so you will basically get a system which efficiency will be greater than 1. Okay. Right. So that means that eta, that means that QH is the alternative definition of, this is QH. If this is alternative expression of eta, so this is basically also greater than 1. So QH minus QC would be greater than 1. So greater than QH. So QC would be minus QC is, so if you do that, so minus QC would be greater than, between minus 3 minus 4 is 0, so QC will be greater than 0. Okay. Sorry, less than 0. Yeah, less than 0. So so basically the QC is basically, so on original, in the original case, like in the original in the ideal case of a reservoir, so where the QC is positive, right? So QC is basically flowing in this side, it should be positive, but in this case QC is negative. So that means the heat is moving onto the opposite direction. Okay, that's why it's like the heat in from hot. So basically the heat is inputting in the hot thing and heat is out from the cold thing. Okay, the heat is flowing like this. Okay, so that's basically the system. Basically the system basically do work without basically deliver, without basically rejecting heat to the colder side. Okay, so this basically means heat in from hot and heat out to cold. Okay. So you're basically cooling out both the reservoirs. The main thing is okay. So this means it's kind of you can extract work while cooling both reservoirs, right? Is the exact thing right is happening here. Okay. So this is a problem. There is negative result temperature Carnot engine. Okay. So this is different things can happen. Okay. Now the next thing that we'll calculate. So we will now check what happens to different thermodynamic quantities. Okay, right? In case of positive or negative temperature, like we have already discussed, right? So all the thermodynamic quantities. Okay, let me write it. So all the statistical thermodynamic quantities expressions we have derived is applicable to t less than 0 as well as to t greater than 0. So this is a condition. Okay, now so okay, yeah. So now we will check this thing. Okay, we will see different thermodynamic. We'll start from the partition function, then we'll check entropy and all. What happens like in positive temperature, negative temperature, high positive or high negative temperature, what happens to the system. So we'll start from the partition function. Okay, effect of t greater than t less than 0 in thermodynamic quantities. Okay. So we'll start from the partition function. So the expression of partition function looks like this, equal to summation over gz e to the power minus beta ez. Okay. So we can write it like this, gz e to the power minus ej by abt. We'll start from the partition function. So let's take a simpler system, the most simplest system, which is a two-level system with basically 0 and epsilon its energy level, and let's take the degeneracy G0 as 1 and G1 is also 1. The single degeneracy, not single, it's basically there is no degeneracy there, non-degenerate level basically. So in that case, the expression of the partition function would be 1 plus to the power epsilon kt. Let's suppose there's only single particle is there in this two-level energy system. Okay. Now for this system, what will happen if you take T, you want to check the temperature at very extremum in the extremum cases. Okay. So first we'll check the temperature at positive 0, when the temperature tends to positive 0. So in that case Q would be 1 plus e to the power, if 1 by 0 is there, so it will become minus infinite, so it gives you equal to 1. There will go 1 by to the power infinite, so 1 by 0, 1 by infinite gives you basically 0. So this gives you basically 1. If t tends to infinite, then Q basically gives you 1 plus e to the power uh, minus e. T is infinite, so 1 by infinite is 0. So e to the power 0 is basically 1. So 1 plus 1 equal to 2. Next thing is t tends to minus 0. If it tends to minus 0, then q equal to 1 plus e to the power plus infinite, right? So e to the power plus infinite means tends to very high value, right? Very high value. So when temperature of a partition function tends to minus 0, tends to reach 0 from the negative side, then the partition function would be show a very high value. Okay. Next we will see t tends to minus infinite. So if t equal to 1 plus e to the power minus e to the power minus infinite, so minus minus it can cancel. 1 by infinite is basically 0. So this basically gives you 1 plus 0 is 1 plus 1 to the power 0 gives you 2. Okay. So if you draw the diagram, it will be looks like this. So if you draw the diagram, let's suppose this, sorry. Let's suppose it's t equal to 0. Now when you take the system to temperature close to 0, you can see from the positive side it will tends to value. If suppose q value is there, so it will has the value equal to 1. Okay. So this is 1 equal to 1. So equal to 1 equal to 2, here is equal to 1 equal to 2 is there. So if the values is t equal to 0 from the positive side, the values goes to 1. Sorry. Yeah. So 1. So t values is 1. And if you increase the value, this is 1, this is 2. And this is if you increase the value very close to t to the power infinity, then in this case the partition function values moves close to 2, like this. It will move like this. Now in the next case, from the other side, if you take the temperature very close to 0 from the negative side, that the entropy, this is the partition function q, this is the temperature, so the partition function tends towards the infinity. Okay, so it tends towards the infinite, and if you increase the system in the negative way, then it will asymptotically trying to reach the value 2. Okay, this is how it will behave at t equal to 0, t equal to 0 and t equals to infinite. Okay, partition function. The next would be, we will be calculating we'll get how the behavior of the partition function for extremum temperatures. Now next will be, we will be calculating the internal energy. Okay, so the internal energy expression you already know. Now comes internal energy. So internal energy, second thing, q is basically 1 plus e to the power minus beta epsilon. This is the partition function. If you know the partition function, the internal energy. Sorry, this should be writing back. That Q is basically 1 plus e to the power minus beta epsilon. It's the expression of the partition function Q. And from here, U minus U0 would be minus n by Q del Q by del beta at constant volume V. Okay. So now Q expression you already know. Now from here, if you this is the expression of the internal energy, we have derived it earlier. Now if you do the derivative, U minus U0 would be simply minus, so del Q del beta would be minus epsilon would become outside, so e to the power minus beta epsilon. The whole thing is divided by 1 plus e to the power minus beta epsilon equal to minus minus will become plus n e to the power beta epsilon by 1 plus e to the power beta epsilon. So this would be the expression of the internal energy of the system. Okay. So now from here, what you can do here from here, just before doing anything, let me just simplify the whole thing. So U minus U0 would be, if I multiply e to the power beta epsilon on both numerator and denominator, you will get e to the power beta epsilon plus 1. And now from now on, now we will check this limit of internal energy at extremum cases, right? So first extremum cases would be in the case where t tends to 0, that means beta tends to infinite. So in that case, this u would be simply n epsilon, so this would be this beta, this tends to infinite plus 1, this whole thing to the by infinite, so this would be simply tends to 0. Now at t tends to infinite, so that means beta tends to 0, so for that case the internal energy would be n by epsilon. Now if beta tends to 0, that means so e to the power 0 plus 1, so that gives you ne by 2. E to the power 0 is 1, so 1 plus 1 is 2, so that is 0.5 into n epsilon. Now if t tends to minus 0, that means approaching the 0 from the negative temperature side, then the beta would be also tends to minus infinite in that case. Then u would be simply n e by e to the power, so minus infinite plus 1. So if e to the power minus infinite, that means 1 by infinite, so 0. So ne by 1, so it will gives you ne epsilon, right? The next is t tends to minus infinite. If t tends to minus infinite, beta tends to minus 0. So yeah, so if beta tends to minus 0, that means the internal energy u would be simply an epsilon e to the power minus 0 plus 1. So e to the power minus 0, whether it's e to the power minus 0 plus 0, it gives you one value. So 1 plus 1 gives you 2. So this is simply that means the internal energy will converge into the value 0.5 into n epsilon. Right? Here also it was 0.5 into n epsilon. Now if you put this whole perspective in terms of the internal energy versus temperature graph, then this whole graph will looks like this, right? This is the internal energy versus the temperature graph. Okay, so one second. So let me do like this. Okay. So 0.5. So temperature is, so internal energy basically changing from 0. Okay. So let me take, this is 0. This is 0.5 into 0.5 into n epsilon, and this is n epsilon. Okay. So what happened when t tends to infinite? So what we see, when t tends to 0, t tends to 0, beta tends to infinite, the internal energy tends to 0. Okay. That means the internal energy will come closer to 0. Now, if t tends to infinite here, t tends to infinite here, beta tends to 0, then the whole internal energy will asymptotically reach the value 0.5 into n epsilon. In n epsilon, that means the graph will looks like this. Right, the graph will looks like this. Next thing is when when the t tends to minus 0. When the t tends to minus 0, beta tends to minus infinite. In that case, the internal energy reaches to the value n epsilon. Okay, so n epsilon means this value. When temperature, this axis is the basically the temperature axis. This axis is the temperature axis, and this is the internal energy axis. Okay. So for t tends to minus 0, the internal energy proceeds to the value in epsilon, and when the t tends to minus infinite, then the internal energy approaches to the value 0.5 n epsilon, or just similar when the t tends to plus infinite. Okay, so both the cases of t tends to plus or minus infinite, the internal energy approaches to the same value. Okay, so in this case, the graph will looks like this. Okay, so this is basically the how basically the internal energy will be a function of temperature in case of a two-level system. Okay. Now, okay, so we got the expression of the internal energy. The last thing that we want to discuss is the entropy. Okay, last thing will be the entropy. So, 1, 2, 3. 3 is the entropy. So entropy would be this entropy. So entropy expression would be S equal to U minus U0 divided by the temperature plus Nk log Q. Okay. So this is the expression of the entropy. So now, similar way, first what we have to do, we have to substitute the expression of the internal energy and partition function in the expression of the entropy, which basically gives us this T into e to the power beta epsilon plus 1, and in this term it will be log of 1 plus e to the power minus beta epsilon. Okay. So this is basically the expression of the entropy we got here. So okay. So now first thing it will do similar way, t tends to 0, beta also tends to 0, beta tends to infinite, sorry. So if beta tends to infinite, so so this would, so S would become, this part would be 1 by infinite epsilon. This denominator terms also tends to infinite. Here also it will tends, then in this term also it will tends to infinite. I mean the denominator. So that gives you basically tends to 0. If t tends to infinite, beta tends to 0, then the entropy would be, so the first term beta tends to 0, so 0 e to the power 1 by 1, 2, beta tends to 2, it will become n epsilon. So t tends to, so n epsilon by t, so t is also there, right? So 1 by infinite, so this term will become 0, plus here, so this will be n log, so e to the power beta epsilon, so beta tends to 0, so e to the power 0 is 1, so 1 plus 1 is 2, so this will become, there's a k is there also, right? Kb, yeah, kb is there, kb. So this gives you n kb ln 2. Next you will do is t tends to 0 minus, so beta tends to minus infinite. This, in this case also, n epsilon to the power to the infinite, minus infinite, whatever, n epsilon to minus infinite. So this also tends to 0. Lastly, t tends to minus infinite, so beta tends to minus 0. In this case, S would be simply, here also n epsilon will be negative, n epsilon to the denominator would be infinite, so this term will become 0. And here n kb in the logarithmic term, 1 plus e to the power beta minus epsilon minus minus 1 by infinite is there, so e to the power 0, e to the power 0 is 1, so 1 plus 1 will give you 2, so it will also gives you n kb ln 2. Okay, here if you draw the graph, okay, if this is the value, if this is internal, this is the entropy, let's suppose, and this is the temperature plot, the temperature, this axis, entropy is in this axis. Now if this, suppose the value in kb ln 2, and this is the value 0. Okay, so what happens when the temperature tends towards 0, this entropy values also tends towards 0, and when the temperature tends towards infinity, the entropy tends also towards the towards n kb ln 2. Similarly, in negative also, negative case also, when t tends to 0 infinite, the entropy tends to 0. Similarly, when temperature tends to infinite, then the entropy also tends to n kb ln 2, like this. This is how the entropy versus the entropy versus the temperature graphs looks like for both the positive and negative temperature. Okay. So here the thing is, this is continuous. Okay, so previously you can see there is a discontinuity here. You can see the there is a discontinuity here for in the case of internal energy, or also for the partition function, there is a discontinuity there at t equal to 0. But here there is basically no discontinuity. Okay. So the thing is, S is continuous at t equal to 0, which is not the case for the internal energy and the case of entropy. Okay, U is not continuous at t equal to 0. Similarly, here also U Q is not gravity mass at t equal to 0 degrees. Okay. So till now we have discussed what is basically the negative temperature means, and how it basically affects, how can we achieve the negative temperature, how like thermodynamic system will behave when it basically comes in a contact of a in contact of negative temperature. And also we have discussed how like different thermodynamic quantities like entropy or the partition functions or the internal energy basically shows different kinds of behavior on like different temperature ranges, extremum ranges. And in the next case we will discuss the canonical ensemble, okay, the concept of canonical ensemble. Okay. So far, let me write it. Canonical ensemble. So far what we have discussed that uh, so far what we discussed that the formulation, the whole formulation that we derived is considering the constraint that the particles are basically non-interacting with each other, right? So each energy levels of the particles are fixed, okay. There are not any kind of interacting energy levels are there. So we basically multiply the particles number with its corresponding energy states in order to get the total number of to, to get the total energy value of the system, right? But what happens when the particles are trying to interact with each other, right? Like in the most, like in the in a practical system, the particle will definitely interact with each other, right? And because of that, at every instant of time, the energy of the system will change. Okay. So for this kind of system, the regular the regular the formalization that we have used till now will not be applicable for this case, for this case where the particles are interacting, right? So for this case we will consider a concept that is known as a canonical ensemble. Okay. So uh, so in canonical ensemble, like we are treating the interacting particle, okay. uh, we are interacting the interacting particle as a member of the ensemble, okay. So now right now we will consider the interacting particles system as a member of ensembles, okay. Members of ensemble means we will basically replicating that whole system into different members, okay. Like different instantaneous energy of the system can be happened. So we will like consider all of the possible uh, energy values of of the ensemble, and we'll like put it together, okay, and check which of the which configuration is the most probable configuration, okay. So let's suppose there is a particle, there's a system with closed system, okay. Closed system means sorry, not closed system, system with interacting particles, okay, with particles number n, volume v at temperature T. So the particles will change its temperature, change its energy, right? So each ensemble will consider. So let's suppose we take some n number of ensemble of the system, of that particular system. One ensemble, two ensemble, NVE, NVT, NVT, third ensemble. This is also NVT, and each of this ensemble has some different energy. It says E1, it says E2, it says E3, like this. All the type of configurational energy that can happen in the system, we are taking all the configuration. So can we put it in different members in an ensemble? Okay. So these are basically the ensembles. Now these ensembles are basically, all these identical ensembles are basically all the identical members of ensembles are closed system. Okay, so that means that they are thermally connected. So they basically equilibrated at a particular temperature T. Okay, so let's suppose the total number of ensembles. So let me first write the let me first clarify the notations. Okay, so total number of particles is total number of particles is n. Okay, and total number of ensembles. Okay, total number of ensembles we are denoting as n tilde. N tilde. Okay. Similarly, let's suppose total energy, like if we add the energy of all the ensembles. Okay, total energy of all of the whole ensemble, we are denoting it as E tilde. Okay, if we add the energies of the members of the ensembles, then the total energy would be E tilde. Okay, now our first thing that you want to do, just the similar way that we have done, in the very first lecture, like we find out the most possible distribution out of all other distribution, right? So for in this case also we want to find out what is the most desirable configuration or most desirable members out of all the members which resides into the ensemble. Okay, so let's suppose out of this n tilde numbers of total members, actually, so the total members of ensemble. Ensemble is a single word, single thing. This whole thing is called as an ensemble, and each of this thing is termed as the member of the ensemble. Okay, each of the system inside the ensemble. Okay. So now let's suppose n1 tilde of ensembles is having energy E1, n2, I mean n1 members of ensemble has energy E1. Similarly, let's suppose n2 tilde members in ensemble has energy E2. Similarly, in this way, let's start from n0. Okay, n0 will be 0. So if you do it in this way, same way, we want to find the configuration. The configuration looks like this. W tilde would be n tilde factorial by n0 factorial, n1 factorial, n2 tilde factorial, likewise this. And a similar way, if you find out the highest distribution, the most probable distribution of this particular configuration, in the same way that you have done into a very first class, like where you have take the log of this distribution, then you take the derivative of the log of the distribution equal to 0. From there we got a particular distribution which is known as the Boltzmann distribution, right? So in here also, if you do the same derivation that we have done in the first class, you will get the similar type of a Boltzmann distribution. So here also the most probable distribution looks like this. Ni tilde would be n tilde equal to e to the power minus beta epsilon ei into q. Here q is the microcanonical partition or microcanonical partition function of beta ei. Remember, here ei is the total energy. Each member of the ei is the total energy of ith member of the ensemble. Okay, total energy ei, which is this microcanonical partition function is actually different in different compared to the normal canonical function or the translational canonical function that we discussed previously. Right there, we are considering one system, and inside that one system we are considering the what is the partition function of that particular system. But here, not a particular system, we are considering the partition function of the whole system, whole ensemble, and that whole ensemble is constituted from many numbers of individual systems, right? So this definition of the microcanonical ensemble is different. Okay. Partition function. So now here also similar way, you can calculate the same quantities, the internal energy, the entropy and all. The same way you can calculate here also. Okay. So the internal energy would be same. Okay, so let's suppose the total energy, in order to calculate the internal, you need the total energy. So each let's suppose ni number of members in the ensemble got the energy ei. Then if you divide it by the total number of what is called total number of members in the ensemble, that basically gives you the average energy in each members of the ensemble. So this basically gives you the similar kind of value, which is 1 by q into del d beta of e to the power beta epsilon, which is nothing but the q. Okay, yeah, q, the capital Q. You can write it like this. Also minus is there. Del beta of ln q at constant volume. Okay, so this is the expression of the average energy of each of members in ensemble. Okay. Next come the internal energy. Okay. Oh, so internal energy we have already derived. This is basically, if you put this thing into perspective of internal energy, this gives you 1 by q del beta at constant value. So this is it. Next thing, similarly, you can calculate the entropy. Uh, so entropy would looks like this. The previous entropy expression. Uh, so we can actually calculate. Okay. So let's suppose. Uh, so each member, inside each member of an ensemble, there is some average distribution, right? Average weight W, like this member is also have W1, W2, like this one. So if you want to calculate the total weight of this whole ensemble, then this total weight, which we are considering as total weight, WEIGHT, total weight would be W tilde, which be simply the multiplication of the average weight of each member in the ensemble, right? It will be equal to the average, sorry, the multiplication of average weight average weight of each member in ensemble. So this would simply, W tilde means, that means if suppose that average weightage is E, average weightage, let's suppose is W, then W tilde would be simply W to the power n. W will be simply W tilde to the power 1 by n. Okay. So if you write, for a single member, if the entropy is looks like this, ln W, for the whole, we can write this thing in terms of the whole ensemble, the weightage of the ensemble also, right? It will be W tilde 1 by n. So this will gives you A by n, n tilde, right? N tilde. N tilde is the number of the members. Yeah, n tilde. ln W tilde. Okay. This is the expression of the entropy in terms of the total weight of the ensemble. Now, similar way, the entropy can be derived in terms of partition function. It will be like this, plus A ln Q, capital Q. Okay. So this is it. So now, okay, so now let's suppose let's do a very quick problem. Okay, how to calculate this answer. Let's suppose a two-level system is there. A two-level system is with single particle. Okay, Now for this kind of system you want to calculate by the internal energy and the entropy by calculating the partition function of the system. Okay. So how can you do that? Okay. So let me first do it. Let me first draw the system. So this two-level system with energy, let's suppose E and energy with 0. Okay. So a single particle is there, only one particle is there. So what are the possible combination? What are the possible ensembles that can happen with the system? The one ensemble is the particle. Let's suppose this has degeneracy G1 and this has degeneracy G0 and G1. Okay. So the first case would be the particle is in state 0 here. Okay, 0 and E, G0 and G1. This would be one ensemble with energy, total energy 0, right? And another ensemble would be, this is ensemble, this is the members of the ensemble. So member 1, this is member 2. The second member of the ensemble would be where the first particle would be into the excited state 1 and zeros, and the ground state remain vacant. Okay. So here the total energy, here C total is 0, here E total is epsilon, right? Now for this this system, if you want to calculate the partition function, the what is called this micro-canonical partition function. So the micro-canonical partition function, which is written as a capital Q, would be simply the first case. The system is in G0 plus e to the power eta into 0. The E total is 0, right? So for the first member, the contribution is this, and from the second member, this is G1 into e to the power minus beta into E. Okay, this comes from the second member. Okay, so the microcanonical partition function. So the microcanonical partition function looks like this: G0 plus G1 e to the power minus beta epsilon. Okay. So this is basically the expression of the microcanonical partition function of a system. Okay, like this contribution comes from the first member, this contribution comes from the second member, and this is the total partition function, right? So now you can easily calculate the internal energy. The internal energy is already we know. That is the what is the expression of the internal energy? Minus 1 by Q del beta, right? So in this case it would be 1 by G0 plus G1 e to the power minus beta E. If you do the derivative of Q with respect to B, this gives you G1 epsilon, minus will cancel, e to the power minus beta epsilon 1. Okay. So internal energy would be G1 e to the power minus G1 epsilon e to the power minus beta epsilon plus G0 plus G1 e to the power beta epsilon. This is the expression of the internal energy. This is a quick problem that we've done for a microcanonical ensemble. Okay, so the possible these are the two possible energies. First we have considered, right? Then from there we have calculated the microcanonical ensembles, and this is the partition function of the microcanonical ensemble. From there we have calculated the internal energy. Okay. So yeah, so this is a simple problem. So now we comes to the end of today's tutorial. So today we have started with the negative temperature. What is the concept of the negative temperature? And from there we have see some problems how the negative temperature is affecting the thermodynamic property, the distribution of particles in the system, and from there we calculate what happens to thermodynamic quantities when it comes in contact with negative temperature, both positive and negative extremum cases. And at last we have discussed the concept of canonical partition function and like different thermodynamic quantities for a canonical partition function, and we have checked this thing through an example also, example problem. So okay. That's it for this class. Ending the meeting.